In the previous video, we talked about Ampere's law. In this video, I want to apply Ampere's law to solve this important case, the current carrying wire. In the current carrying wire, I want to find the magnetic field that a wire carrying a current produces. Now, to use Ampere's law, we know that Ampere's law tells us about the summation of the projection of the magnetic field along a curve times a delta length of that curve summed up all the way around. And that summation we're found is equal to mu naught, the permeability of free space, times the amount of current that penetrates a surface bound by your curve. Well, to make Ampere's law useful, you need to know the shape of the magnetic field lines so that you can choose a curve that goes along those field lines. In the case of the current carrying wire, fortunately, I do know the shape of the field lines. They are concentric circles around a current carrying wire. How do I know that? Well, I know it because I studied it, and I know it because I can put a compass up there and see it. The fact is, it's been measured. All right? So if you put a set of compasses, you would find that they go around in their direction when you turn the current on in a concentric circle. And that there are additional circles. For instance, if you go further out, the field lines will circulate here and again come back upon themselves in a concentric circle around the wire. Now what I want to do is take, of all the circles on all the field lines, I want to take one that includes the point P that I want to calculate the magnetic field for. If you don't know what that point is, you simply make it a point that's at some distance r, an arbitrary distance, from the center of the wire. Now, because the field lines go along there, B is constant. So it's a constant on my concentric circular path. Theta is 0 degrees, so cosine theta is 1. I remind you that theta is angle between delta L, that is the small piece of the path at any point. So for instance, maybe this little piece right here, that's the path, but the field lines are also going in circle, so that's the field lines. So they are lined up, the angle between them is 0, so the cosine of theta is 1. This enables me to simplify Ampere's law down to this important equation here. The magnetic field times the distance along the path. That's because I pulled the B out, and all I'm doing is summing up little pieces of length along the path until I get all the way around, and then that's the length of the path. So B times L is mu naught. The amount of current that goes through is simply I in this case, a single wire. But L is 2 pi r. The circumference of my path. So now we solve for B and we get mu naught I over L, or that the magnetic field is mu naught, the current, divided by 2 pi r. And this is the solution for the magnetic field of a current carrying wire. All right, I'll see you on another video.